Hey gang, in this video we're going to do another example of a t-test. Here we go. According to the CDC, the Center for Disease Control and Prevention, the average weight of American babies at the age of 5.5 months is 7.63 or so kilograms. Meanwhile, a 2005 randomized experiment performed by a team of researchers from New Zealand compared the growth of infants that were fed different types of formulas. It's pretty interesting. We're not going to use all of their data, but what we are going to use is a sample of their 36 infants that were fed a cow milk-based formula. So these 36 infants that were fed this formula had an average weight of 7.87 kilograms, forgot to write that there, with a standard deviation of 0.9 kilograms. And we're going to compare that sample to the published average weight for American infants at that same age, 5.5 months. Okay. And before I get too carried away here, I want to actually show you these websites where I found this information. So I was able to extract this info from the CDC website. I'll put the link in the video description, and also here is our study that was performed by New Zealand researchers. Let's write down all of our known information before we get into hypotheses and test statistic. Let's just get it all written down. The sample info, that's the information from the New Zealand study. Let's write down the sample info. Over here, we've got the sample mean and sample standard deviation. Just so it's super clear, I'm going to write that over here. And this is in kilograms. The sample size was also given. There were 36 infants. So that's N. Okay. Remember, we're going to compare this one sample to a previously established or some other baseline value, and that is the average weight published by the CDC for American infants. So that is the value that we're comparing this sample to. So that's the value of mu that's going to go in this null hypothesis. And this is all in kilograms. Okay. Before we get into the testing procedure here, let's consider what type of information we've got. The variable of interest for this example is, well, what was measured, what was observed in each of the 36 infants, right? The random variable here is their weight at 5.5 months. That weight is a quantitative variable. Furthermore, it's continuous. So we have sample stats that apply to a quantitative variable. So we're not going to do a proportion test. This has to be a t-test for a population mean. Let's talk about some of the testing requirements for a t-test. We saw that for a confidence interval for a mean, there are certain requirements, and those are essentially the same here for the t-test. We need to have a random sample or a randomized experiment, and we were told that that was the case here. Furthermore, we need independent observations, and the way that is sometimes assured is that the sample size is a small portion of the population size. So here, our sample size is less than or equal to 5% of the population size. We weren't told the population size, but certainly 36 infants is a small portion of all infants from New Zealand. And lastly, we need the sampling distribution to be normally distributed. We were not told that this data follows a normal distribution, but the central limit theorem can be implemented because our sample size is at least 30, and that assures that the sampling distribution of the sample mean of x bar is approximately normally distributed. Those are important requirements for the validity of the t-test. Let's now set up the null and alternative hypothesis. As mentioned, this is regarding a population mean, mu, equals for the null hypothesis always. And this is the baseline or pre-published value that I've got written here in pink. That is the value that we're comparing our sample to. So I'm going to write that number twice. And are we going to do a left-tailed, right-tailed, or two-tailed test? Well, we were not explicitly told either of those options. So since we're going to do a comparison, and there's no indication that the babies from New Zealand fed the cow milk formula might weigh more or less, we're just doing a comparison, we're going to go ahead and do a two-tailed or a non-directional test, since there's no inclination to do directional. The next couple steps are our computational steps. We're going to compute the test statistic and then the p-value to state the conclusion. I'm going to copy-paste the test statistic formula right here. And we've got all the appropriate inputs up here. So let's rock and roll. Our test statistic, t, the sample mean weight after 5.5 months on this formula. We're going to compare that to the average weight published by the CDC, 7.63 or so kilograms. In the denominator, we need the standard deviation of the sampling distribution, S over square root of n. Let's pump that into a calculator. Okay, I feel like I was diligent enough there. I made a couple mistakes, but I rectified those, and our test statistic is about 1.45196. Okay, I like to do a little visualization of our p-value before we go and compute it. Remember, we had that little applet, so it's going to be quite easy for us, but it's good to visualize. This p-value is an area in the t-distribution. It's the probability of observing a test statistic like the one we got, 1.45-ish, or something more extreme. In this case, because we have a two-tailed hypothesis, we look in both directions, right? Because of symmetry, these two areas that we want are going to be the same in both tails, right? So this green region that I'm going to shade right here. Okay, and so that is the probability if this null hypothesis were true. This is the chance of getting a sample like the one we got. We're going to go use an online applet to quickly determine this p-value. Before we go there, we need to know the degrees of freedom. And degrees of freedom is not too shabby. It is simply the sample size minus 1. Okay, we got sample size up there, 35 then. So this would be the t-distribution with 35 degrees of freedom. We are ready now to go and compute with an online tool our p-value for this test. We saw this website in a previous video. I'll link it again in this video. We want to put the degrees of freedom in the first box, and in the second box is our test statistic. And I'll round it to right there. And in the third drop-down menu here, we need to choose whether we're using a right-tailed, left-tailed, or two-tailed test, and so what region do we want? This first one is indicative of only a right tail. The second one would only be left-tailed. The one that we want is the one that has the doubling occurring. If we look closely, if your test statistic was positive or negative, this formulation would always work. The absolute value of your test statistic, that's our 1.45-ish over here, and the area to the right, and then there's a doubling occurring, so it's getting that symmetric region on the left here. So that's it. That's our p-value, 0.15542. Those are our computational steps, but we still need to state a conclusion based on our analysis thus far. To state our conclusion, we are going to compare our p-value to the level of significance. And while it was not stated earlier, we'll use the default or most typical significance level of 0.05 for alpha. P-value about 0.155 alpha. Okay, so which is bigger, p-value or alpha? Certainly the p-value is larger. Okay, so what is the appropriate conclusion then? Do we reject the null hypothesis, or do we not reject the null hypothesis? Take a moment, think it out. Okay, if you haven't figured it out, pause this video. But remember, when the p-value is low, the null must go. So here, our correct conclusion is going to be that we do not reject the null hypothesis. This is our correct conclusion based on our p-value. Now let's interpret this conclusion. This is a very technical, jargony conclusion. I want to provide an interpretation that can be read by most individuals without having taken a statistics class. So here I've got sort of a multiple choice action going on here. I want you to read these and tell me which one would be correct. Writing these conclusions on your own takes a little bit more practice than identification of one that's already written. So before we make our choice, let's just do a recap of what this problem was all about. The American Centers for Disease Control has this published weight for infants at 5.5 months old. Here, this sample from New Zealand, we are comparing this sample to this other baseline value. Turns out the sample was not particularly different than that published value, which is why we got a test statistic which was not particularly large, which is why we got a p-value that was not particularly small. So our sample of 36 infants and their average weight was not that different. Okay, let's check this out now. So read carefully, pause this video, and read these two options and tell me which one is the correct option. Okay, I'm assuming you have paused and made your choice. Hopefully you notice that there is only one word different between these two options. And that one word is this word not. Here, we're saying the data suggests there's a difference. Here, this is saying the data does not suggest that there is a significant difference in the average weight of the 5.5-month-old New Zealand infants who were fed the cow milk-based formula compared to the average weight, that baseline value from the CDC for the same aged infants in the US. Okay, which one is it? A or B? Hopefully, because you did not reject the null hypothesis, that means there is not evidence for the alternative. The correct option here should be B. I got a follow-up question for you. Did we just prove that the null hypothesis is true? Let's see. We just said the data does not suggest a difference. Not a difference. Doesn't that mean that they're the same? No. Because we're not just detecting a difference, we're actually detecting if there's a significant difference. So did we just prove the null hypothesis is true? Absolutely not. No. We're not saying that the New Zealand infants weigh the same as the American infants. We are not saying that they weigh the same. And in fact, on average, they don't, right? 7.63 versus 7.87 kilograms, they're not the same. But they are not significantly different. So chew on that for a little bit. We do not ever prove a hypothesis, null or alternative. Here, we failed to reject the null hypothesis. We failed to reject HO. That does not mean that HO is true. This does not imply proof that the mean weight for the infants in New Zealand is 7.630425 kilograms. That does not imply proof that this is true, but just that there is not enough evidence to suggest otherwise. Another possible way that you may consider this is the old phrase where the absence of evidence does not imply is not the same as evidence of absence. You may have heard of this. Here in this case, with the weights of the babies in New Zealand compared to the US, on average, we're not saying that they're the same. We just don't have enough data to definitively or confidently say that their average weights are different. All right, this is going to conclude this video.